Hi, my name is Mario Juric.
I'm Petar Zecevic, or you can call me Peter.
And we're going to be talking about a tool called AXIS, which stands for Astronomy Extensions for Spark and Astronomical Data Processing of the LSST. And I'll tell you in just a second what that is with Apache Spark. So before we begin, let me just, we just wanted to give you a quick introduction of who we are. As I said, I'm Mario. I'm a professor of astronomy at the University of Washington, and I'm here to represent the user of this machinery that we have built, or that Peter has built mostly. What I do is I do large data in astronomy. So if it doesn't have at least 10 million rows, I'm usually not interested. That's kind of the scales that we're talking about, and we're talking about more like billions of rows. Peter, want to say something about yourself?
Yeah, so I'm a CTO from SV Group. That's a small company, about 50 people in Zagreb, Croatia. And I'm also a PhD student at the University of Zagreb, and I've been collaborating with the REC Institute at the University of Washington, which Mario is part of. And we've been building AXIS, the system built on Spark. And I also wrote the Spark in Action book, which came out in 2016. It's kind of a little bit outdated now. The second version should come out soon. So yeah, that's about me.
All right. So to give you a little bit of context and introduction, what we're trying to do here is we're trying to find a way for astronomy to work with or to survive and thrive in a data deluge that's about to hit us over the next 10 years. And to give you some introduction about that, I want to tell you about large survey astronomy and how it's really revolutionizing astronomy. This is something that's happening now, that started happening over the last couple of years. What is a survey? If you go to Google and type in survey, this is what you get back. In our case, we care about this second definition. It's a general view, examination, and description of somewhere and something. Essentially, for astronomers, a survey is when you go out and try to catalog everything that's in the sky and write it down and then try to infer what's going on with the universe. And astronomy has a super rich history of doing surveys. Actually, it started back in ancient Greece. Hipparchus of Rhodes, this guy, who's actually brilliant for his time, constructed the first star catalog in recorded history containing about 850 stars. And for about 1,600 years, that's what astronomy was. People would try to go to better places, have better eyesight to record more and more observations of just stars in the sky. This has changed in the 1500s with Galileo. So what Galileo is most known for in astronomy is for the quote-unquote invention of the telescope. It's actually not true. The telescope was invented, I think, by someone in the Netherlands. But what Galileo did was that. He realized that if you point it to the sky, you can actually find many interesting things. And so Galileo's telescope allowed us for the first time not just to count how many stars or how many objects, how many planets we see in the sky, but actually to zoom in and see what's going on in detail with every individual object. Now the problem there is you couldn't do that exhaustively for every single object in the sky. So we started going in this, we entered into this two-step that astronomy has been in for the past 400 years or so. You have a survey that constructs a catalog of everything, of all objects in the sky. You focus on coarse classification. You try to find objects that appear peculiar for whatever reason, and then with large telescopes, you zoom in on those and you try to understand from those few representative objects, what are the details of the astrophysical processes that govern them. And this is all time-consuming. This is all something that where you couldn't really cover large swaths, definitely not in the big data sense that I mentioned when I was introducing myself. So most of astronomy has been dealing with, to give you a sense of it, with these large telescope observations, we're talking about in orders of hundreds, potentially thousands of observations collected over decades sometimes. So the history of our field really is this. For about 2,000 years, this was a field that was extremely data poor. It was very difficult to get data. If you had a big telescope, if you could get access on the big telescope, you would spend nights, collect lots of observations, and then your data analysis was actually usually quite simple after that. Now you can imagine where this is going. The invention of CCDs and computers changed everything. So we get to roughly early 2000s, and then this telescope gets built. This is called the Sloan Digital Sky Survey. It was the first modern digital survey in astronomy. And suddenly we go from having an order of millions of things observed through 2,000 years of history to photometry, to measurements of brightness and behavior and precision and position of more than 900 million stars and galaxies. So this is what the SDSS, let's say a visualization of the SDSS catalog looks like. There's about 1.2 billion rows of observations. So the telescope takes images. Those images get processed. That's another talk. Processed into catalogs. Objects get detected, objects get measured, put into catalog. And we suddenly have the ability, instead of fighting for big telescopes to image individual, a couple hundred individual objects in the sky, we have the ability to download the entire sky into a computer, in effect, and have it into a data, and put it into a database and then analyze that big database. So we go from a couple of thousands of objects to easily billion objects as astronomers. And this is where a lot of what we call today data science started in our field. Like Jim Gray had this famous kind of quip about astronomical data that they are very expensive but worthless, because you don't have to worry about, astronomers are really good with sharing data. You collect data, you can share it around. They're very expensive to collect, but nobody is really holding them together. So they're perfect for research of big data analysis techniques. So this has continued. In the previous slide, I don't know if you noticed, SDSS collected about 10 terabytes of data in 10 years. We fast forward about 10 years into after SDSS began. This telescope comes along. It does 700 gigabytes every night. More recently, a European mission that's in space called Gaia published a catalog of 1.7 billion objects in the sky with exquisitely precise measurements of their positions. And where this is going is, in less than 3 years, this acceleration towards data deluge is going to reach yet another level when the Large Synoptic Survey Telescope, a project that's currently being built in the Chilean Andes, is completed. And what LSST is going to start delivering are 10 million alerts every night. So that's a stream to everything that changed in the sky. 37 billion, catalog on 37 billion astronomical sources. And then with each of those sources being reobserved over and over again about 802,000 times. So we're talking about 30 trillion measurements. Well, the way you should think about these is these are all numbers of rows in corresponding tables. So this is kind of what our problem is. And when you have that sort of thing, what can you do? Well, basically you can do almost anything. So the paradigm of astronomy shifted from taking individual observations, taking observations of individual objects, to basically building a few large telescopes that can image the entire sky, put everything into a database, and then we work off of those databases. So from this telescope, we can both look for killer asteroids, and we can try to figure out the nature of dark energy, things that are typically very, very different. Here are the scales this is just a summary of the previous slide. So we're talking about 7 trillion rows for detections, 37 billion for numbers of objects, 10 million for numbers of alerts. Alerts are going to be coming out at 60-second latency. So every 60 seconds, we get about 10,000 new ones. Total image data after about 10 years is going to be on order of 50 petabytes. And after 10 years, with catalogs plus images plus calibrations, are going to be on order of 100 petabytes, 83 says here. So what do astronomers do with this? Once this catalog is available, astronomers love to ask all kinds of questions. And I just mentioned that it might be everything from finding killer asteroids to dark energy. And how is it traditionally done? Traditionally, for example, for SDSS, we took all of these data, we placed them into a big relational database, SQL server for in that particular instance. And then what you would do is you would come up to that database through some web interface, type in your query with the assumption that your query is extremely selective, and perhaps download 1% or 0.5% or 0.1% of the entire data set. You get that locally, usually in a CSV file or something like that, and then you would do your analysis, visualization, and discover wonderful things. So if you're interested, this map is a map of all the small dwarf galaxies that are currently falling into the Milky Way, and the Milky Way is eating them up. We did not know that before SDSS discovered it. Fast forward to LSST. The first challenge with this kind of paradigm is dataset size. So now we're going to have catalogs that are the scale of petabytes. And even if you could, and I'm going to argue that you don't want to, even if you could write that selective query, it would still be an order of tens of terabytes potentially. And that's difficult just to download. Even if you're able to download it, it's difficult to manage locally. So just the sheer dataset size is an issue. The other problem is that LSST is not going to be the only mission in town. There's a space survey mission. There are missions that ESA are building, and all of those catalogs are better if you put them together. If you look at what LSST has seen when at the same time when a different mission has seen something and so forth. And the second thing is the nature of what we're studying has changed. It's not about here is a selected query. It's more about these days I'm going to trawl through all the data, run some machine learning algorithm on it, look for outliers, look for the most interesting objects. So it turns out you will almost always now want to go through these petabytes. There's now, every project generates a couple of petabytes, and there are going to be multiple projects. So things become difficult. And the final difficulty in this is, one thing, you have astronomers who are writing mostly Python and who are not used to any of this. So how do you make their codes that typically run on a laptop or perhaps a small cluster now further scaled by 1 or 2 orders of magnitude to these types of data sets? So we have scalability. What are the frameworks in which we write these codes? And on top of that, even if you could write those codes, what are the resources? So ultimately, the question that we're facing as a community is how you scale exploratory data analysis, because you can do almost anything with these data, to petabyte-sized data sets and thousands of simultaneous users. And this is really, obviously, where Spark enters. So this is where we started collaborating with Petar to try to adapt Spark to basically solve these problems for us in Astro.
Yeah. So thanks, Mario. Yeah, so those are the challenges of the 21st century astronomy. And those are the things that the folks at the Direct Institute recognized as they saw this need for the next generation astronomical analysis tool. And luckily for me, I was just starting my PhD, and I was involved with Spark, and we decided to try to build something together. So out of all these considerations that Mario walked you through, they came with a set of requirements that for this tool needed to satisfy. So first of all, the cross-matching. It should be efficient in cross-matching. That means you need to combine data from several catalogs, because different telescopes, different projects obtain data in different filters in different way. And astronomers want to combine all this to gain more knowledge from all of these telescopes together, if possible. And this is the one of the main things that they do when they do exploratory analysis of the data. They try to cross-match data from multiple catalogs, and that's a challenging thing to do. I'll walk you through this in a moment. And it should be based on industry standards, because such as similar to Apache Spark, because that way it's less risk to build upon such a tool because you have all that community backing. As you probably know, you're part of this community, and you have all those problems solved in large corporations and so on. It should be scalable. It should support many users, and it should provide simple but powerful astronomical API extensions so that it should be built also in Python, which is language that astronomers use almost exclusively. And it should be cloud ready. It should be able to, you should be able to put it on premise or in the cloud. So that's Spark ticks all of those boxes, right? So what is cross-matching? If we have two catalogs, or we can just think of them as Spark tables, we have rows of observations. Those can be stars, asteroids, or galaxies. Each row is one observation. And we put them in this coordinate system based on declination, dec, and RA, which is right ascension. Right ascension goes from 1 to 360 degrees. That's the way telescope spins, and the declination goes from minus 90 to 90 degrees, the way telescopes declines. So we denote the observations from one catalog as dots and the other as axis, and we want to find all of those pairs of observations from first and the second table that fall within some distance from each other. We have some search perimeter based on Euclidean distances. In this case, it's pretty simple idea, right? But we can also use some similarity, for example, how similarly bright they are or something else. We can plug in different measures there. And we denote here on this image, filled circles are a match, so they are close enough together. So it's a simple idea, but when you have a billion objects in each table, it's not a trivial thing to do. So the way we did it, and Access is quite fast at cross-matching, that's because of the efficient data partitioning scheme it uses. And it's based on Jim Gray's, Mario already mentioned Jim Gray. He worked for Microsoft Research. Unfortunately, he died in sailing accident disappeared in the Pacific. But he published lots of papers and left lots of good research behind him. And they divided the sky into horizontal zones of certain height. And they came up with this scheme of a set of SQL queries and indexing schemes to make it faster to do the cross-matching inside the Microsoft SQL Server. So we took this idea and adapted it for distributed architectures. And we're using Parquet files, which are arguably the most often used format alongside Spark, I guess. And we use bucketed Parquet files. If you don't know what that is, you can divide Parquet into one, let's say, file into several physical files. Each of those would be a bucket. And you can bucket a Parquet file by values from one or several columns. So we are bucketing by zone values, and so all the rows that have the same zone value go into the same bucket. And within the buckets, we sort the data by zone and RA columns. And we also duplicate data from the lower thin border line from each zone into the zone below it, because the matching candidates and cross-matching can span the border zones, right? So we want to catch all of those candidates in the neighboring zones, and we don't want to depend on the data from other buckets. We want to do it in parallel, independently, right? If we show it graphically on an example which has only 4 buckets and only 16 zones, in reality we have, default is 500 buckets and thousands of zones. So in this case, all the rows from zone 1 go to bucket 1, and zone 5 and zone 9 and 13 go to bucket 1, zone 2, zone 6 to bucket 2, and etc. So when your Spark application then when you try to join this data from Parquet files, two Parquet files bucketed in this way, and they have to be bucketed in exactly the same way, with exactly the same zone height and the number of buckets. Then each executor, in this case, let's say we have 4 executors, each executor can independently use data only from one pair of buckets, regardless of the other bucket pairs, and they can do it independently of each other in parallel. And if you look at the web UI physical plan in your web UI, or the textual description of the physical plan, this is the ideal case you want to see, where Spark is just reading both files from Parquet and then filtering out, which does nothing actually, and sorting. This sorting step always has to be there before the sort merge join, but it also doesn't do much because the data is already sorted within buckets. And then it's all, just given to sort merge join. If you would see a box saying exchange step here, that's the equivalent of the shuffle in the old, let's say, core Spark. So that's the thing you want to avoid, the most expensive operation right in Spark. So this is the optimal way to join bucketed tables. And that's what we're doing with Access. However, this is more or less the query we are using to join the data. We're using the equi-join, so the equivalence condition on the zone column, but we're also using this epsilon join, which is traditionally called epsilon join, but just a range condition on the secondary array column. In this case, Spark would just first do a Cartesian join of all the rows that have the same zone. And in our case, those can be thousands or millions of rows with the same zone. And this Cartesian join, of course, is not doable. It just breaks, stands still. And only once the Cartesian join is completed, only then does the Spark do the checking for this secondary condition. So it's obviously easy to, there's obviously a optimization opportunity here. So we filed this Jira ticket. We called it sort merge join inner range optimization. So basically what it does in this case, it maintains a moving window over the rows of the right table. As the row from the left table changes, it just removes the rows with values that are outside the window, less than the condition requires, and moves new rows inside it. So it just zips through both tables really quickly, uses the minimum amount of memory and the minimum number of checking for the validity of the conditions. So it's really fast. There are other approaches to do this, to solving this problem. People have been traditionally using hill picks or HTM sky partitioning schemes, which are both hierarchical, and you can dynamically change the level of granularity of how the sky is partitioned, and it allows for defining, for example, complex objects. You can cross-match complex geometrical objects. However, we believe that it's much slower for cross-matching than Zone's algorithm. So these are our results. We published the paper with this. This is the image from the paper. So on all these graphs, the x-axis shows the number of executors, and the y-axis is the running time. So we have a Gaia catalog with 1.7 billion objects and SDSS with 800 million. We can do it in 37 seconds, just plain cross-matching and just counting the number of rows, no further processing of the data. In 37 seconds with the warm cache and 148 seconds with cold cache. All the tests were done on one big Linux machine, not in a cluster. And what we mean by warm and cold, it's not Spark cache, it's the file system cache, Linux file system cache. So cold means that it was empty when we started, and warm means it was preloaded with part of the data. Why part? We know that there's no way that all the data fits inside the memories, but how much was cached, it's difficult to say. And we also have, for example, ZTF dataset with 3 billion rows cross-matched with Gaia. We can do it in 315 seconds with cold cache. It was all done. Those are the best results with, I believe, 28 executors. And Mario will show a demo with deployment on AWS in the cloud, how it runs. So this is an example of using the Access API. We also added some of the often used astronomical functions. So first you need to create a Spark session as you normally would, and then use it to create the Access catalog session, which uses the Spark's metastore DB to store additional information such as zone, height, and things like that. And then you can use it to load the Access frames, which are just Spark frames with several edit functions, such as cross-match, shown here. And to use cross-match, you give it the other Access frame you wish to cross-match with, and the radius, search radius, and then you use it just like any other Spark frame or other Access frame. You can save the results as a new Access frame, or which would partition the data in a way that's usable by Spark, and so on. Of other functionalities, we provide the region queries, which are kind of basic things that astronomers do. You have 2 points, and you want all the objects within the square of between those points. And the cone queries, you have a 1 point with a radius. You want all the objects inside it. Histogram, you give it a condition for building bins and the number of bins, and it returns the data in a format which is good for using in matplotlib. And also for light curve data. Light curve data is when you have multiple observations of the same object. Those are called light curves. And we store those in arrays, in array columns, and we rely on Spark array functions for handling those. And of course, you can use all other Spark functions, such as machine learning or whatever else. Here's another example with computing light curve features using Python UDFs. So you can really do anything you like with those results. So I'll give the word back to Mario.
So we started this about 2 years ago, and we've been using the solution for about a year now to do real research. There's a group of universities, about 10 universities, doing a survey called the Zwicky Transient Facility, which is about 1/10 of LSST. And so what do we learn from this? One is, this is not going to be news to most of you, Spark scales really well. We're actually very pleased with essentially getting linear scaling on AWS to hundreds of executors easily without even having to try much. And the reason why we went to Spark, why I went with Spark, was really one of the big reasons, in addition to scalability and so forth, was the SQL support. As if there's 20 years of history in astronomy using SQLs to do queries, and to bring the community on board, you need to have that kind of thing. And Spark's support for SQL is just fantastic. Now, we did encounter some issues, and I know that the community is really working to resolve them. Efficient data exchange with Python is the key to all of this. So the Arrow project and PyArrow and friends have really helped here and sped this up by orders of magnitude, and things are moving in the right direction. The language barrier is non-trivial, unfortunately. Astronomy kind of lives in the Python world, and for us to hack on Spark is kind of difficult, just because Scala we're not that familiar with Scala or Java or JVM in general. And then pushing Spark into exploratory data analysis is also non-trivial sometimes. The kinds of issues that our users encounter is that sometimes we would, you'd write a query that would work just fine, then your next query ends up taking up all the memory on your executors, and executors start crashing, and sometimes you don't even know that happened, and you're kind of just waiting there for days until you realize, oh, something's wrong. So understanding how we can push Spark, which started more as a batch system, into something that we can give to a user that has no clue that they're running Spark underneath is a challenge that us and many of you, I'm sure, are working to figure out. But overall, this is, I think, a tremendously good experience, and we basically have a tool now that we can scale up to catalogs of orders of tens of billions or potentially trillions of rows over the next 5 to 10 years, and that's pretty good. So we'll stop there and let's take any questions, and then if there's time, I'm going to show you a 1-minute demo of what this really looks like in a Jupyter notebook. All right, thanks.
Great. So I'll just pass the mic around for questions. Yep, please. Okay, here we go. Question number 1.
If you're talking about the epsilon join, at some point you're going to have points which are near the edge of your zone. How do you actually cover that your epsilon environment actually goes into the next partition?
Yeah, I mentioned that we duplicate the lower region at the border of each zone to the border below it. So we have part of the data is duplicated, which increases the amount of data on disk, but allow us to do it independently of the data from other buckets. So we have copies of those points in those zones, let's say.
Any other questions? Don't be shy.
All right, while you're thinking of questions, let me show you a movie. So this is our Jupyter Hub setup. It runs on AWS. Jupyter Hub Jupyter is the main way how we interact with the data. Log in with your GitHub ID, relatively usual stuff. And this is what a notebook would look like. So from the point of view of the user, they would go, say from, usually it's Dirac import database. I created this different module for this demo. From demo import database, you give it the number of executors, you wait for some time while all of that spins up. On AWS, it usually takes, an order of a couple of minutes for them to spin up. Then you load the catalog, you get the handle to the data frames for your catalogs, and then in this example, what we're doing is we're taking 1.7 billion rows from Gaia. We're positionally cross-matching them to about 800 million rows in SDSS. Those are those two lines, and then I plot the result. And it scrolled quickly, but the punchline here is that cross-match took about 3 minutes. So 3 minutes, 20 seconds. So, and this scales linearly. So if I wanted to get it done in half that time, I would have started 64 executors rather than 32. So this is, from the point of view of our users, like astronomers who get this big catalog, want to run through it, want to go find that 1 in a billion object. This is phenomenal because they can quickly do it. If anything crashes, in the meantime, Spark usually takes care of that or restarts, or tries to restart that node. And we can also run it on spot instances, which are cheaper.
Very impressive. Any questions?
All right.
No questions. Then in that case, I'd like to thank all of you and ask you once again to give a thank you and applause to our presenters.